Can you see my screen?
Yes, sir.
Okay, so how do you think of a smooth map? Right. So last time you discussing is smooth map and I mean in local coordinate in concept of a local coordinate in a manifold. And we also said that how if there are two local coordinates on the same point, then what is it? How it changes, or what is the relation between these two? Right. This is nothing but the change of coordinate you have seen in Rn, right? Yeah. So do you agree what I said vaguely? The change about the local coordinate having the same coordinate, having two coordinates at the same place. Yeah, and then it is nothing but the change of coordinates in Rn. Okay. So once you know in terms of local coordinates, you know chain rule, right? Today's which date? So the point is, once we have local coordinates, the concept of local coordinates, the concept of local coordinates, we have the chain rule also. So how does it look like? So you have a map from M to N, let's say F, and there is a map from N to P. So M and P are manifolds, smooth manifolds. So G, and then you look at this map, G compose F, and you can find the derivative. So choosing a local coordinate u, x1, x2, xn, and here let's say v, y1, y2, yn, let's say near P here, FP here, and here W, Z1, Z2, Zn, and this is G of FP belongs to P. Then what you have, you can actually have this G compose F by del x1. So what will be the chain rule? Let's say at P. Well, in the neighborhood of P, so let me write it as Q. So what will be the chain rule here? Anybody? Right, here is this coordinate system. At P is U, x1, x2, xn. The way we defined last time. and the coordinate system around FP is V, Y1, Y2, Yn. And the coordinate system around G of FP is W, Z1, Z2, Zn. Now you have this composition, and of course you cannot have this partial derivative here. So the point is you need to take the one component here somehow, making it, let's say this one, instead of P, let's look at this map. Let's say it goes to R. All right, so you know R, identity is that last scale. So what is it?
Sir, summation over I, dou G P applied on G, dou G of P applied on G over dou yi.
Yi, okay. Yi.
This is evaluated at P applied on G.
Let's say
F applied on G.
And
this is F applied on G.
Okay, F of Q. So this yeah, and then what?
And then dou F G by dou X1.
Dou F?
Dou F Q by dou X1.
No. Here it is ith component, right? So you need to make sense of that. So this is I find, and then you have ith component. So del of F goes from, let's say, this M to N, right? M to N. So here Yi compose F by del X1. Does this make sense? Does this make sense? So if you look at R n to be Rm, which is F1 F2 Fm, right? So it will be F of R del Fi by del X1, right? But that in general in the manifold that might not make sense. So this is Yi compositive. Is this fine? Any question?
Yes, sir.
Any question here?
Sir, but this would depend on like the local coordinates, right?
Of course, you are taking derivative in terms of local coordinates. So it depends on local coordinate. If you change the local coordinate, then you will get the corresponding thing, right? The way you change the coordinate in Rn as well, right? Here, when you did chain rule, even in case of Rn, it is in terms of local coordinates. But in Rn, what happens? Fortunately, the local coordinate is a global coordinate. But one can make change of coordinate, right? And then and look at new coordinates, and the partial derivatives with respect to new coordinate may not be the same as the partial derivative of the earlier coordinates. So partial derivative depends on the coordinates, because yeah, that is where with respect to that you are only taking the derivative. So as a whole, whether the Jacobian part, Jacobian derivative is non-zero or not, that does not depend on the local coordinate. But the partial derivative, each partial derivative does depend on the local coordinate. Yeah, any other question? Is it clear now? These partial derivatives depend on the local coordinate. But when you say something, let's say M and N are of same dimension, and you want to say the concept of Jacobian, right? And not just Jacobian. Jacobian is non-zero. So that part is independent of choice of coordinate. Okay? Being non-zero is independent of choice of coordinate. determinant of the Jacobian non-zero. So there are some things which are, though it depends on local coordinate as an expression, but it might not be dependent on the local coordinate as a whole. But in this case, it does depend on the local coordinates. When you change the coordinates, the partial derivatives, values of the partial derivatives will change. Any other question? Now, what about inverse function theorem? Yeah, can anybody say the statement of inverse function theorem from Rn to Rn? Yeah.
If we have a point in Rn and the determinant of the Jacobian is non-zero at that point, then we can find a open set around that point U and an open set around the image of that point. So if the point is P, then we are talking about f of P. So say that open set is V. So f maps U bijectively to V, and so there will be an inverse, and the inverse will be C1, provided we start f being C1.
All right. Right. So let me state it in a simple sentence which is easy to remember. Okay. Let f from Rn to Rn. Well, it need not be from Rn to Rn. So let's say, right. So let's write it omega to Rn. Omega is an open subset of Rn. So this is C infinity. So I'll consider C infinity. Though it is the amount of smoothness you would take, you would get back that much smoothness. C infinity map. If so, f is a local diffeomorphism at P in omega if and only if the Jacobian del f j by del xk, this matrix jk is at P is invertible. Make sense? Makes sense. So what do you mean by local diffeomorphism? So this term, local diffeomorphism, this term means that there exists a neighborhood U of P such that f from U to Fu is a diffeomorphism. Yeah. So local diffeomorphism means this one, right? This part. So now it is easy to remember, right? And local diffeomorphism, this is diffeomorphism. It's just, I mean, the smoothness. Diffeomorphism in general, diffeomorphism means you have if you consider C1 map, then the inverse is also C1. But if you consider C infinity map, inverse is also C infinity. In our case, we are considering inverse is C infinity. So well, let me change for this one. So you just consider C1, so it's a diffeomorphism. C1 is. So f is differentiable, inverse is also differentiable, and derivative continuous. Right, now it is easy to remember.
F of u has to be open, right?
Of course.
Don't we have to additionally state that, or did we get that automatically?
You get it automatically, right? If it is a diffeomorphism, automatically you get. So once you show this, there exists a neighborhood U such that this is a diffeomorphism, then I mean under a diffeomorphism is an open map, right?
So F inverse
Yes.
continuous, so it has to be open.
Right.
No, sir, but that would just mean that f of u is open in f of u.
Well, this is f of u is no. It is actually. I mean, well, f is actually a map from omega to Rn, right? So f of u. I mean, you are in some sense right, but the point is here in this case, u and fu both are. I mean, u is an open subset of Rn, right? So I mean, this f of u is automatically you don't need to worry about that. I mean, you check. So I suggest you check that if u is open, that comes automatically. You don't need to assume that. There exists a neighborhood U and there exists neighborhood V that side. That part is not needed. Just a few is good enough. Look at the proof of implicit inverse function theorem. Again. And you see that if you can prove if U is open. You can take without loss of generality to be V to be f of U. Okay, so check that. Look at the proof again. This would be a nice exercise.
So in the statement of inverse function theorem,
Yeah.
we actually say that there is a map from F U open to V open. So we explicitly say that, right?
Yeah. But look at the proof.
Yes, sir.
Look at the proof. You actually do not need to say that. The other side will be open. So you can prove actually in the proof, you are constructing a neighborhood V, which is nothing but the image of U. All right. So look at a proof and see if you get into any problem, you let me know. All right. Any question?
Sir, can you repeat why you took
Yes.
C1 map instead of C infinity in the start?
So it's basically, I mean, diffeomorphism. So what definition did you give? Did you give as a diffeomorphism?
Sir, I think it was C infinity.
Okay, so the point is, it is nothing. If you look at K here, CK, then one says CK diffeomorphism, and sometimes you know it's understood which category you are looking at, whether C1, C2, and C infinity. So you can actually, I mean, in the differential geometry, most of the cases, almost all the cases, unless explicitly mentioned, we are working in C infinity map. That's why we are saying the C infinity. Otherwise, if you look at C1 smooth maps, and you can say this, I mean, diffeomorphism in that category as C1 diffeomorphism or just diffeomorphism. So people say diffeomorphism, and whether in which category it is it is looking, I mean, one is looking, it should be clear from the context. It is generally clear from the context. Okay. So whether C infinity or C1ness, it depends on what. Yeah. So the map F you are taking, whether you are working in C1 map, if you are looking at C1 map and you are talking about diffeomorphism, then it is C1 diffeomorphism. If it is a C2 map and you are looking at a restriction of that as diffeomorphism, then it's a C2 diffeomorphism. So inverse function theorem actually gives back the amount of smoothness you take, it gives back in the inverse also. Does that answer your question?
Yes, sir.
Okay.
Sir?
Yes.
I mean, in the proof, we are constructing a U such that such that f of u is open in Rn.
Yeah.
But when we are stating the theorem, when I'm writing f from u to f of u, it's a diffeomorphism. It is slightly weaker than saying that f from u to f of u is a diffeomorphism and u and f of u are open in Rn. Right. So I think we should separately say that, because otherwise we are stating a weaker result.
Which one? This one weaker result?
What I'm trying to say is like f from so u is an open set and f from u to f of u is a diffeomorphism wouldn't imply f of u is open in Rn. So like stating that f of u is also open in Rn will which will technically make this theorem, I mean, giving us a stronger result.
Local diffeomorphism, yeah. So I mean, you can say that there exists a neighborhood V of P and there exists a neighborhood V of Fp, and then if u to V is a diffeomorphism. Local diffeomorphism, the definition is like that, and it is onto also. So you get f of u. Yeah. So the point is f is defined from omega to Rn. It's already there. Okay. So I mean, here if you write, I mean, there exists a neighborhood V u of P and let's say V of Fp such that f of u to V is a diffeomorphism, right? That's what you're concerned, right?
Technically, just I want to add one sentence to what you wrote, that f of u is open. That's it, in Rn.
No, I mean it's automatically it's clear from the context. So f of u is a subset of Rn. Do you agree with that?
Yes, sir.
No. Right? And it is diffeomorphism to an open subset of Rn. Right? Do you agree with that? So it is open. Yeah? It's still not clear.
Okay, sir, I'll think about it. And
Yeah, think of it. So U is open subset of Rn and f of U is a subset of Rn that is there. It's not outside Rn. If it is outside Rn, then you might have some trouble. Right? Now diffeomorphism would say that f of U is open subset of Rn actually. Yeah, so now I want to write the inverse function theorem in terms of, in the case of manifold. So what should I change? So inverse function theorem for manifolds. Suppose if M1 and M and N are two smooth manifolds of dimension m and n respectively, and f from m to n is a C-infinity map, then f is a local diffeomorphism at P if and only if well del I want to write the following del the matrix is del well if and only if well before that
So we
need
need
to
to
ask.
fix like some coordinate, right?
It's actually true for any coordinates. So I need to mention the statement, I need to mention the coordinates. So it is true for any coordinates, but uh, so let u x1 x2 xn be a coordinate chart at P and B y1 y2 yn be a coordinate chart at f of P, then f is a local diffeomorphism if and only if the matrix, I need the coordinate here, right, to write the matrix. So this is y j compose f del yj compose f by del x or by k, let's say. This is fine. Del yj compose f by del xk. Jk at p is invertible. Right? Is the statement clear to you? It's nothing but the statement as it is in case of Rn, right? Nothing new. All right? So nothing new as you see here, right? And by the time I guess some of you already have thought about the proof, right? Yeah, can anybody suggest a proof?
So because it's a C infinity map, we have the composition phi inverse f and then psi. Like if we go the whole way around, that should be C infinity. And then we're looking at that guy's matrix from Rn to Rm. We're looking at that matrix and we're telling it's invertible.
Mm-hmm.
And then we're applying inverse function theorem of real uh, thing over there.
Right. That is true. So we need to look at what matrix we are basically looking at, right? To prove. So you have here M, let's say M here, N here, P is a point, and you have a coordinate system here, right? U, this is FP, you have a coordinate system here, V, and this is the map, F. Now this is a map, let's say, this gives you the coordinate system, of course. This is, let's call it phi, by which you take it to some Rn, some open subset of Rn, and here it is psi. goes to some open subset of Rn. All right. Now, what? Of course, this picture should be in your mind. Now, let us look at what we mean by this partial derivative del of yj compose f by del xk. All right. Del of yj compose f by del xk at p. So what does it mean? So this was, what is it by definition? Come on, X is a coordinate system there in the manifold, right? What is its definition?
Sir, apply phi and then do partial with RK.
Apply? What? Apply?
Phi, compose Yj, compose F with phi.
No, this is a phi inverse. And then del Rk. Again, I missed. You should have remembered, right? So this, I messed with the notation. Last time we fixed the notation, right? Yeah, I messed with the notation. So this was upper xn. Otherwise, when you read the book, it will be in trouble. Y1, Y2, Yn. So here you can put J. This is true for any J. This is I. Yi compose F makes J. For J equal to 1 to N. This I have taken up to M. All right. Similar thing here. X1 up to Xn and Y1 up to Yn. Then this one, just subscript gets changed to superscript. Yj compose F xk. All right, let's get back. Okay, so now this one. Del yi or yj compose F with del xk. Right. So now this one is nothing but, by definition, del by del Rk Yj compose F compose phi inverse. Right. So R1, R2, Rn, the notation was, it was subscript or superscript? Was this the notation? consistency of notation is very important. So that's why I'm a bit careful here. So what notation did I put last time? Is okay? Was it downstairs or upstairs?
It was upstairs.
Yes, sir.
Okay. Okay. So now what is it? Again, you can write something, right? So what is yj?
Ri applied on psi.
Right. So del by del rk rj compose psi compose f compose phi inverse. Right. Now what is this map? This one. Psi compose f compose phi inverse. Right. So we are looking at the jth component of that map. Right. So that means this is invertible. This matrix. So what it gives is del yj compose f by del xk at p jk invertible implies Jacobian. So yeah, let me write it to step. So this is del by del rk rj compose psi compose f compose phi inverse at pp jk is invertible. Right. Now that is nothing but the Jacobian of psi compose f compose phi inverse, right? Phi p. The Jacobian determinant is non-zero, right? Yeah. Or the derivative. You can write the determinant of the derivative at f. Determinant of the derivative psi compose f compose phi inverse at pp is non-zero. All right, then we can apply inverse function theorem. The inverse function theorem for Rn to get psi compose f compose phi inverse is a local diffeomorphism at phi p. This implies this if and only if f is local diffeomorphism at p. All right. Any question here? So last part, if you are not convinced yet, so go back and write this out. The definition, local diffeomorphism and local diffeomorphism here, and the smoothness of f, then you will see this is nothing but the same thing. All right. Okay, so what is next? So what it answers is the following remark. The previous theorem tells us when a collection of functions f1, f2, f1, f2, fn, let's say f1, f2, fn, where fj is a map from m to r, right, forms a coordinate system at p in n, where so M is a manifold here. So if you have a manifold M and you have some manifold of dimension n, let's say, and you have f1, f2, fn, n many functions, and now you want to ask the following question: whether this f1, f2, fn is a coordinate system. All right. Then what do you need to check? You need to check the Jacobian, whether Jacobian determinant is non-zero. That would give you a good enough reason or good enough argument to see that those functions form a local coordinate system, right? So here, coordinate system here, this means locally around P. You have a neighborhood, and this f1, f2, fn are the coordinate system. Clear?
So here M has dimension n, right?
Yeah. So maybe I should put it here, where M this and M is a manifold of dimension n. Yeah, right. So it is the number j. I mean, the number n is the dimension. Yeah. Another question? Okay. So let us go a little bit from the smooth maps and see something which might be a little more interesting to you. So now the question is: suppose M is a manifold, and it might have group structure as well, right? So does it give you any other interesting object? So manifold, first of all, Rn, you look at Rn. Rn has a lot of structure. It has group structure, it has um, vector space structure actually, and it has metric space structure. All this combined together. Now when you see the manifold, the vector space structure is gone, right? Locally looks like Euclidean, and then you have some diffeomorphism, then the homeomorphism, and then one can define smooth map over there as well. Now suppose vector space structure is gone, but maybe there is a group structure. Can you say anything? What extra properties should I get? Well, we'll see more about what extra property you'll get. But now let us give a definition, sir. This is a new concept. If you have a manifold with a group structure, that's called Lie group. And Lie was the first to study it. A Lie group is a smooth manifold. A Lie group of dimension is a smooth manifold of dimension n and with a group structure, with a group structure such that the group operation PQ goes to is coming from, let's say, G cross G to PQ G and P G to P inverse in G are both C infinity map. You might have heard about topological group, right? Yes. Have you heard about topological group?
Yes, sir.
Yeah. So what is what property you have in topological group?
These maps were continuous.
Right. These maps are continuous. Now this here, these maps are smooth. So for Lie group, these maps are smooth. So yeah, it has some interesting property. We'll see probably. But before that, for now, we'll just have few examples. On Rn with pose class structure. Rn is a Lie group with group operation as addition. So is that maybe I should write the following maps instead of group operation. So second thing is, let's say C star with multiplication is also a Lie group, right? Now, when you say something like this, what comes to the mind is what happens if we look at matrix group, right? So third, GLNR, collection of n by n invertible matrices with real entries. Right? Does it form a Lie group? Or how does it form a Lie group? Any ideas? First of all, is GLNR a manifold?
Yes, sir.
Yeah, maybe Arundhati say the reason. Why is it in manifold? Yeah, looks like she is gone again. Abhishek, can you say the reason why is it manifold?
Sir, GLNR is uh, homomorphic to uh, subset of Rn, I think.
Sir,
So, so it's a manifold.
Homomorphic to Rn.
I think I forgot.
No.
sir,
Yeah,
Rn
Arundhati.
square.
Yeah.
It's isomorphic to Rn square.
GLNR is isomorphic to Rn square.
No, I mean we can define a continuous map from matrix A to determinant of A. That maps matrix A to determinant of A. So we can realize the space of matrices as as Rn square.
No. By determinant, you want to realize it as a, subset of Rn square. How?
No, I mean the space of matrices can be realized as Rn square because there are n square entries in a matrix.
Right. Fine. After that,
Uh,
you are not considering all the matrices, right?
no,
So,
This is open set in Rn square.
right, it's an open subset of R square. How is it? Why is it open subset?
You can define the map from Rn square to R by assigning two determinants.
Then,
By the
yeah, you define.
isomorphism Mn set of all matrices to by Rn square.
Then, how do you get it as an open set?
Sir, it's an inverse of 0 to infinity, open 0 to infinity.
Is it true? Inverse of open 0 to infinity?
This is the inverse
Inverse of R minus 0.
inverse function
R minus
from
0.
Rn square.
Right. It's inverse of non-zero points, right? R minus 0. That's an also open set, right? Determinant is non-zero, but it may not be positive. It may not be negative all the time, or may not be positive all the time. So you look at R minus 0 and look at its inverse. So this is an open subset of Rn, so it's a manifold. Open subset of Rn square. Since GLN R is or can be thought of is homomorphic to an open subset of Rn square GLNR is a smooth manifold. Now, why is this two maps are continuous? Or sorry, smooth? Yeah, maybe I should leave it as exercise. Why are
Sir,
yes?
because should I say?
Yeah, you should. Yeah, speak.
So like when we are multiplying two matrices, then each component of the resultant matrix is a polynomial.
Right. Right.
So it's all the components are polynomials, so hence smooth.
Why is that so?
All the component maps are smooth.
Yeah, all the why is the component maps smooth?
So I'm looking at it like in Rn square.
Right. So if you look at this as Rn square map from Rn square, so you need to look at a chart, right? Chart
Yes, sir.
is just identity, and corresponding that side also you look at identity and then look at each of the components. And we proved actually what would be the smooth map. It is if you show that each component is smooth, then the map is smooth. In that case. So in this case, you have polynomials. So these are smooth. But if you want to write it, you just need to write this expression of each entries of AB and A inverse, and show that this is the polynomial and it's smooth. All right. Okay. So any question if you have, or now we'll have the exam. Yes, let's talk about it.